So an ellipse is also defined in terms of distance. An ellipse is defined as all ordered pairs are all points whose sum of distance to two fixed points is constant. Sum of distance to two fixed points is constant.
Now for this one.
So what I'm going to do to illustrate this is draw a grid where I'm going to put two ordered pairs here and here. Instead of a focus, we're going to call them foci because there are two of them. And I'm going to put a point 4 units of, because I'm choosing 4, that I know is the same distance to this point as it is to this point. In fact, the way I've gridded this out, you can actually figure out what those distances are, but I don't want you to think in terms of that just yet. We're going to call that distance A, so that the sum of the distances, is equal to 2A. Now, I'm going to start gridding some of this out. So I'm going to actually decide that this right here is another ordered pair called the center. And this unit here, this distance between the center and the focus, we're going to call little c. And the distance between the center and this point that I'm going to call an m is called b. And to get a visual for what the ellipse looks like with these conditions, I'm going to actually draw the ellipse that would be what these conditions would show. This is an ellipse where every single ordered pair has the same sum of distances to those two places. And it's not too difficult to show that that sum of distances, since it's constant, is 2A. I mean, we see that here from this point. But what is challenging is to show that when that point slides to where it's right here, that the distance from this point, which I'm going to call V, to the focus 1 plus the distance from this point to focus 2 is actually the same as the distance across from vertex to vertex. You can see that by taking this little piece here and sliding it all the way over to the other side. So what that means is that that entire distance from vertex to vertex is equal to 2A, which means that the distance from C to V is also A. I'm going to keep that out of the figure for right now, but I do want that to be kind of known, and that will be important much later. This is called, right here, the major axis. And the major axis has a length equal to 2A. Okay, I could make this a really easy derivation for the formula for an ellipse by calling the center 0, 0, but let's be more challenging. Let's make this center be equal to HK. If you don't like the derivation, you can skip ahead on the video, but I encourage you to watch it to see kind of where this is going. The focus would then have coordinates of x plus h, or sorry, not hk, it'd have coordinates of h plus c, h plus c, comma k, and h minus c, comma k. And I'm going to put an arbitrary ordered pair here, call that xy. And if an ellipse is defined as all the ordered pairs where the sum of the distances, so x minus h minus c squared plus y minus k squared, so that's the distance from here to here, square root, plus then the distance from here to here, which is x minus h plus c squared, plus y minus k squared, and that sum of distances is equal to 2a, as we saw right up here, and with that original one we drew. So this is some fun algebra for you guys. We have to try to manipulate this to get to a better form, and the only other trick at this is that in this right triangle right here, I see that a squared is equal to b squared plus c squared. So you guys are in honors class. Let's derive the formula. We're going to square both sides and move this radical over to the right side. And if I square the left side, what I get is x minus h. Well, I can actually get this to be in a better form. Instead of x minus h minus c, let's make it x minus h plus c. But that's still going to be squared plus y minus k squared equals, again, moving that to the other side and then squaring the right side means foiling, which is going to seem a little complicated, but it's nothing we can't do. I have 4a squared minus 4a times that big radical, which I'm going to write as x minus h minus c squared plus y minus k squared. And then we have a lot of terms to kind of throw down in there, plus, so again, I moved that radical over and I squared both sides, so I get x minus h minus c squared plus y minus k squared. And you can see the y minus k squareds drop out. So now on the on all this, I kind of need to do some manipulation to make this a little bit easier. Why don't we square this and this so I can see what terms remain and which terms drop out. So I'm going to get x minus h squared plus 2c x minus h plus c squared equals 4a squared minus 4a radical x minus h minus c quantity squared plus y minus k squared plus, and then I have x minus h squared minus 2 times c times x minus h, and then plus c squared. So that helps because now I actually have some cancellations here, 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 and here. And if I move some of these terms around, I could move the this over to the other side and get 4c x minus h is equal to 4a squared minus 4a radical x minus h minus c quantity squared plus y minus k quantity squared. Those all have a 4 in them, so we're going to cut the 4's out, divide both sides by the 4, and now because of where I am with this, I want to isolate the radical, and let's square both sides a second time. So to isolate the radical, I'm going to get c x minus h minus a squared is equal to negative a square root of x minus h minus c squared plus y minus k squared. Finally, we get to square both sides a second time. So when I square the left side, I'm going to get c squared x minus h squared minus 2 times a squared times c times x minus h plus a to the 4th equals a squared, and then this came out of the radical, so x minus h minus c squared plus y minus k squared, and that's all in parentheses. Whew. Keeping your algebra straight yet? We're going to go multiply all of this in, and I'm going to multiply this out, which I have not been doing yet. So on the right side, I'm going to kind of make this as, let's keep the a squared, x minus h squared minus 2c x minus h plus c squared plus y minus k squared. Left side, I still have all this c squared x minus h squared minus 2a squared c x minus h plus a to the 4th. Next step is going to be to distribute. So got to keep this left side the same. The right side, I'm going to distribute the a squared, so I have a squared x minus h squared minus 2a squared c x minus h plus a squared c squared plus a squared y minus k squared. And I did that because now this cancels out. Okay, we're actually starting to bring these terms down to something a little bit more manageable. I'm going to subtract the x minus h's over to the other side, or this term over to the other side. Like this term's going to swing over here. Still have the plus, or no, let's move the a to the fourth over the right side. So then on the right side, I have a squared c squared minus a to the fourth. Oops, got to slide this over to the right. Forgot my minus a squared y minus k squared. And let's make sure that's c squared, and we're okay. All right, group this, factor in x plus h squared out, and I get c squared minus a squared. Then I have minus a squared y minus k squared. We're going to factor in a squared out and get c squared minus a squared. Why is that valuable? Because, oops, according to one of our original conditions way up here, that c squared minus a squared is equal to b squared. So I get b squared x minus h squared minus a squared y minus k squared is equal to a squared b squared. And if I divide both sides by a squared b squared, I'm going to get x minus h squared over a squared minus y minus k squared over b squared is equal to 1. And my only slight issue is that somewhere in there that's supposed to be a plus sign, because I did the derivative for hyperbola. That'll be fun to try to figure out where that is. I'm going to pause it for a second. Ha! I found it. C squared minus a squared. Well, if I know that a squared plus b squared, or is equal to b squared plus c squared in this problem, then c squared minus a squared should be negative b squared. Those were negative. So let me just kind of do a quick fix here. Those were negative b squared. This is also negative b squared, which means that everything was positive, which means that this is a positive. Whew. I had to teach a class in between, so would have found that. Okay, so this is the master form for the equation of the ellipse. And that's a big thing that you guys have to have memorized. This is actually the form right here. I'm going to erase the little highlight for a horizontal ellipse, meaning one that is stretched horizontally. If I want a vertical ellipse, all I have to do is switch the A and the B. A vertical ellipse puts that like this. And now I have a vertical one. And since A is defined as the distance from C to V, B is defined as the distance from C to M, and C is defined as the distance from center to the foci. Because of the way we define these, A will always be larger than B. A is the bigger distance. So really the one we're calling A squared is whichever one's the larger number. This is so simple in practice that don't overthink this. Okay, let's go back up here and let me kind of explain this from the visual here. A is defined as the distance that I'm going to highlight in blue from center to vertex, which happens to be the same as this distance right here. C is defined as the distance from center to focus, and B is defined as the distance from center to the M's. I'm going to stop calling them M's and V's. V's are going to be major vertices, and M's we're going to call minor vertices. We also have a major axis, which has a length of 2a, and we have a minor axis, which has a length of 2b. So we're going to define one more quantity here in a minute, but I want to graph an example of this. So I'm going to graph x minus 1 squared plus y plus 2 squared over 100 is equal to 1. And note that there's an invisible over 1 here. So what I'm going to first do is identify A equals, B equals, and C equals. A is the square root of whichever one is the largest, so that's equal to 10. Then B is the smallest, it's equal to 1. And C is equal to the square root of 100 minus 1, or the square root of 99, which is 3 root 11, which is about 9.9. In a case like this, you need to look at this and see that the bigger number is underneath the y, which means that it's going to be a vertical ellipse. So since it's a vertical ellipse, let's actually start to graph these things that we know of. So I'm going to put a grid down, and actually, yeah, I want to make sure this is large enough here. Okay, that should be large enough. And let's figure out where the HK is, or the center. The center is at the order pair 1, -2. Those values are determined by the x minus h and y minus k. So that goes here. A is 10. So I want to go, you know what, I'm going to change my grid to be a little bit smaller. I do need much more space than I have here. Okay, apologize, let me redraw my grid. Okay, so 1, -2, zoom in. A is 10, which means I'm going to go 10 up and 10 down. Oh, lost count. Here, 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 here. Okay, there we go. And I'm going to put V's for my vertices. I'm going to go 1 to the right and 1 to the left. Those are the M's. And then I'm going to go 9.9 up, and I know I had to exaggerate this for the foci. People ask, why do we have to graph the foci when they're not really points on the ellipse? The fun part for me is actually connecting and graphing the ellipse itself. Sorry, it's doing that thing where it's moving it to where the cursor is, but let's graph the ellipse first, and I'll start to address the question of why we have to graph the foci, even if it's really, really difficult to get them exact. So here's the ellipse. The foci are actually the most critical points on the graph. Foci are where the sun is when you're talking about the elliptical orbit of a comet. The foci really determine what's happening. So keeping that in mind, I want to kind of make sure you remember the relationship here. A is the biggest one, so a squared is equal to b squared plus c squared in an ellipse. And another final point that we're going to talk about is this value called the eccentricity, which is defined with a little e, which is stupid because e is the base of the natural log, as c over a. It's a ratio of the distance c over a distance a. In this case, the eccentricity is like 9.9 over 10, which is very, 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 very close to 1. If the eccentricity approaches 1, you get something that looks like this. If the eccentricity approaches 0, what you get is something that looks more and more like a circle. I'm going to try to do this, use this tool to kind of get this, there we go. So that's kind of a little eccentricity there for you. You may be asked to calculate the value of the eccentricity. In this case, this would be 99/100ths, or 0.99 about. So that's there for you to keep in mind, that the eccentricity is a number that determines how thin the ellipse is. Okay, let's do number 2. 9x squared plus 25y squared minus 36x minus 50y plus 60 equals 0. First step is that you have to complete the square on x and y. So I'm going to put the x terms together, and then I'm going to put the y terms together, and I'm going to move the negative 60 over to the right side. I'm going to group the x terms and the y terms, and then I'm going to factor a 9 out, giving me x squared minus 4x. Complete the square on the x, gives me a plus 4. Then we go on to the y, where I'm going to factor a 25 out. Y squared minus 2y. Oh, hey. 25 out. Y squared minus 2y. Complete the square with a plus 1. Equals negative 60. I add plus 36. And then plus 25. And that gives me, let's see, so I have 9x minus 2 squared plus 25 y minus 1 squared equals 1, which isn't quite the form I want, but I can change this with a little trick. This is really x minus 2 squared over 1/9 plus y minus 1 squared over 1/25 equals 1. That means that the larger of the two, the a value is 1/3, the b value is 1/5, and the c value is the square root of a squared minus b squared. And that would be 1/9 minus 1/25, or 25 minus 9 over 9 times 25, which is square root of 16 over 3 times 5. Or sorry, 3 times, yeah, this should be 3 times 5. Hang on one second. Sorry, I had an athlete trying to tell me something. 9 times 5, so that's 3 times 5, 15. You get 4/15, which is a silly one to kind of graph, but we'll try to do it. So we're going to sketch this as best we can. I realize that this is going to be a little bit tricky, but it's going to be really, really, really tiny. So our sketch of this is going to include a center at 2, 1, because of the HK. There is no quiet in this building. Okay, then we go up, and now this is wigging out again. Okay, center at 2, 1. Let's see, a value, this is a horizontal stretch, so I need to go 1/3 over. Well, if I'm going to actually do this right, let's cut this down. Let's change the grid. View. Okay. 2, 1, and I want to go right 1/3. We'll put that there. Left 1/3. Put that there. Up 1/5. We'll put that there. Okay, stop with the interruptions. Down 1/3. We'll put that there, and there we go. That's kind of a poor indication of it. I can try to draw it with a tool here. That's a little bit better, but I'm not even going to try to graph where the foci are. Just put like little dots there and say, see, look, the c value was 4/15. Finally, the eccentricity, which I'm going to just abbreviate ECC, c over a is equal to 4/15 over 1/3. And 4/15 over 1/3 is equal to 4/5. So close to 1, closer to 1 than 0. It doesn't take much to get some eccentricity on these things. So that's it.